All right, today we're diving into one of the most powerful tools in all of science, mass spectroscopy. Seriously, this is a technique that lets us see the invisible and weigh the unseeable. It's all about answering one fundamental question. What is this stuff actually made of?
So picture this. Imagine you're a detective at a molecular crime scene. You've got this tiny unknown sample, could be anything. To solve the case, you have to know exactly what it is with total certainty. So how in the world do you weigh something you can't even see? Well, the answer is a machine that's basically a hyper-accurate scale for molecules. Mass spectrometry is hands down the best method we have for figuring out not just a molecule's weight, but also what elements are in it. It is the ultimate tool for identifying the unknown.
Okay, so here's how we're going to break this down. First, we'll talk about the molecular fingerprint problem. Then we're going to go inside this incredible molecular scale. We'll see how you turn a molecule into an ion, watch the great ion race, and then learn how to read the results. And finally, we'll get into why this technique is such a game changer.
First up, let's take a journey right into the heart of the machine. We're going to follow one single molecule all the way from the beginning to the end, just to see how this whole thing actually works.
You know, for all its complexity, the entire process really just boils down to these 4 key steps. First, you have to vaporize your sample, turn it into a gas. Then, you ionize the molecules, which means you give them an electric charge. Next, you separate those charged molecules or ions by their weight. And finally, a detector counts them up. That's really the whole thing. Vaporize, ionize, separate, and detect.
Okay, let's zoom in on that ionization step. This part is absolutely crucial because the machine can only see and mess with particles that have an electric charge. So every single molecule that goes in has to be turned into an ion first.
Yeah, this is the fundamental rule of the game. Without a charge, a molecule is just a ghost in the machine. It's completely invisible. By turning it into an ion, we make it visible to magnetic fields that are going to do all the heavy lifting and sorting for us. Now, what's really cool is that scientists get a choice in how they do this. They can use a really energetic method, like electron impact. Think of it like smashing the molecule with a hammer. It shatters into a bunch of pieces, and that pattern of pieces is super useful for identification. Or they can use a softer method, like chemical ionization. This is more like a gentle nudge that keeps the molecule in one piece. That's perfect if you just want to know its total mass.
Okay, so our molecules are all charged up and ready to go. Now it's time to sort them by mass, and we do that with what I like to call the great ion race. This is where the magic of separation really happens.
So how does this race work? Well, the ions get blasted into this powerful magnetic field. And that field acts like a sharp turn on a racetrack, grabbing onto those charged particles and forcing them to curve.
And just like on a real racetrack, mass changes everything. The lightest ions, they're like these nimble little sports cars. They can zip around that tight curve no problem. But the heavier ions, they're more like big, heavy trucks. They have more momentum, so they swing out wide on the turn. And just like that, this difference in their turning path separates them perfectly by mass. Pretty clever, right?
Now you're going to see an equation pop up, but don't panic. All this is really saying is that by controlling the magnetic field strength, that's the H, and the voltage that gets the ions moving, that's the V, we can figure out the exact mass-to-charge ratio, the M/E, for any ion based on how wide its turn was. It's just the physics that makes this whole sorting process so incredibly precise.
So the race is over. The ions have been sorted. Now what? Well, at the finish line, there's a detector, and its job is to count every single ion that hits it. And that data produces the final result, a totally unique molecular fingerprint.
And what you get is a chart that looks something like this. It's called a mass spectrum. Each bar you see represents a different piece or fragment of that original molecule. Where it is on the bottom axis tells you the fragment's mass, and how tall the bar is tells you how much of it there was.
And here is the absolute key to everything. This pattern, it is totally unique. Just like a human fingerprint, no two compounds will ever produce the exact same mass spectrum. This is what makes it possible to identify a substance with absolute certainty.
So when scientists look at this fingerprint, they're looking for specific clues. They look for the molecular ion peak. That tells them the weight of the whole original molecule. Then you have all the fragment ions, which are the pieces it broke into. And they always look for the base peak. That's the tallest one, and it shows the most common fragment. You put all those clues together, and you can figure out exactly what the mystery substance was.
Okay, so we've seen how the machine works, which is amazing. But let's talk about the big question. Why does this molecular scale matter so much out here in the real world?
Well, it really comes down to three huge advantages. First, its sensitivity is just unreal. It can find a needle in a haystack of haystacks. Second, it's incredibly accurate, giving us super precise molecular weights. And third, it's reproducible, which means the fingerprint for a substance is the same every single time. That makes it an unbelievably reliable tool.
And that power is used everywhere. I mean it. Geologists use it to figure out how old rocks are. The petroleum industry uses it to analyze gasoline. In forensics, it's a workhorse for identifying drugs or trace evidence at a crime scene. And environmental scientists depend on it to find tiny amounts of pollutants in our water and air.
At the end of the day, mass spectrometry gives us this incredible power to answer the simple, fundamental question, what is this stuff? And as the technology gets smaller and faster and easier to use, you just have to wonder, what new mysteries are we going to solve when we can point a device at literally anything, anywhere, and instantly know what it's made of? The possibilities are just mind-boggling.